Suppose I have some point pairs. So these are xy points. So like for example x equals 0 and y equals 25 here. X equals 1, y equals 27, so on and so forth. I can take this information and I can plot it on a Cartesian axis system. For example, 0 and 25 is that point. 8 and 41 looks like it's somewhere over here. 3 and 35 is here. And then 1 and 27 is here. And all these points fall on these points, all of them essentially fall on a line, just like this. So we can say, since all these points fall on a line, that this is linear data. So let's set this up in a table here, this information. So we got 0 and 25, and look at some interesting ideas. 1 and 27, 5 and 35, and 8 and 41. And let's look at the average rate of change between each of the points. See what we see here. So we recognize this as linear data. Let's see what the average rate of change between these points gives us. So the average rate of change is 27 minus 25 divided by 1 minus 0. Call this m. This is 2 over 1. That equals 2. Okay, between these 2 points, the second and the third point, we've got m equals 35 minus 27 over 5 minus 1. 35 minus 27 is 8. 5 minus 1 is 4. Again, this is 2, interesting. And then finally here, we've got m equals 41 minus 35 divided by 8 minus 5. 41 minus 35 is 6 over 3 equals 2. So all of these, the average rate of change between all of these is 2, which means the slope between these are 2, what we could call the slope. And essentially, this equals some, between each of these 2 points, you've got some rise over some run. M equals rise over run, and we call this the slope. Okay, so we look at this orange line, and we can see that this thing has a domain of all real numbers, has a range of all real numbers too, and it looks like y is a function of x here, because we can do a vertical line test where we were to take a vertical line anywhere here. Then we would see that for any given x value, we have only one y value, and we can move this vertical line anywhere along this orange line, and that would be true. So this, in fact, is then a linear function. Furthermore, I see that I can describe this linear function with this relationship. F of x equals the slope times x plus b. So in the case of the problem up above, the slope is 2 times x plus, and b, what is b? Well, if we think of this, if we imagine that x equals 0, this term will fall away, then the value of our function when x equals 0 is 25. So this is 25. We call this b. Because of that, we call this the y-intercept. It's the place where the function intersects the y-axis. And that always occurs when x equals 0. So this is 0 here. When x equals 0, we could go negative here, or negative down here in the y direction. I guess the scale's different though. And this is probably closer to -2, as this is 2 and this is closer to -30 here. But as we go, anytime we cross the y-axis, x is 0. So x is always 0. That's how we find the y-intercepts. Now these linear functions can come in 3 different varieties. We could have an increasing function. In this case, our slope is positive, going uphill. We can have the decreasing function. Here, m is negative, or going downhill from left to right. And finally, we could have a constant. In the case of the constant, m equals 0. So this is increasing, decreasing, and constant. So for the most part, this is all review. We've done this before. In the past, we would say, suppose we had a line, and we chose a point x1, x2, then for the x1, we would have a y1 value, and then for the x2, we would have a y2 value. So the slope was the difference between y2 and y1 divided by x2 minus x1. But another way of looking at this is the slope equals, so y2 is really a function of x1, and y1 is also a function of x1. This is actually a function of x2. So we could say then for our relationship, this is a function of x2 minus the function of x1 divided by x2 minus x1. Just another way of looking at it. No real changes there. But this all really just is, we have like a delta y over a delta x, change in y over change in x, or a rise over a run.